Hello, and welcome to this video on how Heron derived his formula for the area of a triangle. So, who is Heron? Well, Heron was also called Hero of Alexandria, and he lived in Alexandria, Egypt during the beginning of the 1st century, which was also an era of great change from the ending of the Greek Empire to the takeover of the Roman Empire. Heron studied the Greek mathematicians of earlier years as well as the Babylonian and the Egyptians' contributions to math. And he not only was a great mathematician that links us to the past, but he also was an innovator, an innovative inventor, engineer, and scientist. And above all, he was also an inspiring and entertaining teacher during his time. Now let's take a look at how he developed his famous formula. We know, as well as other mathematicians of Heron's time, that the area of a triangle is found simply by finding half of the base times the height. What Heron proposed was that we could find the area of a triangle without knowing the altitude or the height of the triangle. In Heron's unique way of teaching, he would begin by trying to solve a specific problem instead of a generalized method that could be used for any triangle. So he might look at a triangle with the side lengths of, let's say, 13, 14, and 15 and try to generate the area. And then he would approach the problem from a generalized point of view, such as the early Greek mathematicians would have done. So he would have used, let's say, sides A, B, and C. This is the formula that's now called Heron's formula. And what the formula says is to find the area of the triangle, you just need to find the square root of S times S minus side A times S minus side B times S minus side C, where S is equal to the semiperimeter. And the semiperimeter is just found by adding A, B, and C sides together and finding half. Now, Heron was given credit for the development of this formula, but it was actually discovered much earlier by Archimedes. And much of Archimedes' work was lost and then rediscovered later. And Heron published this formula in his book Metrica, which was a collection of the math knowledge of the ancient world. Heron is remembered for this formula so much that a special type of triangle has been given his name, the Heron's triangle. And what a Heron's triangle is just a triangle in which the length of the sides and the area are integers. So let's take a look at the previous triangle with our side lengths of 13, 15, and 14. And let's see if this is a Heron's triangle. So we would first need to find the semiperimeter by adding the three sides together and dividing by 2. When we do that, we get 21. Then we would just plug in our variables into his formula and to find the area. So here's our semiperimeter, here's side A, side B, side C, and working that we see that we get the square root of 7,056, and the square root of 7,056 is 84. So this triangle is indeed a Heron's triangle because we have integers for the side lengths and we have an integer for the area. But how do we prove the Heron's formula for the triangle ABC? Well, we could divide the triangle by the altitude straight down the middle and get two triangles. We could use the Pythagorean theorem, and we could then use algebra and manipulate variables to prove Heron's formula. We could also use trig functions to find the length of the sides by the angles. But what we're going to do is we're going to attempt to prove his formula the way that Heron did in the 1st century using Euclid geometry. Now, on Euclid geometry, let's open this up real quick. Switch programs real quick. Euclid geometry says that you can use a compass and a straight edge to do your work, to find your axioms, but he would not have used the measurement side of a straight edge. A straight edge was just used to make straight lines. And so we're going to take our triangle ABC and we're going to see how Heron took a look at it. I'm going to kind of fast forward through this. But what he would actually do is he would bisect the three angles of the triangle. The angle bisectors, then we would find that midpoint. And he made three smaller triangles using what's called the end center of the triangle. And then he would find a perpendicular intersector from I for each of the sides. So we're going to find, let's speed this up. So we're going to find a perpendicular intersector for each of these triangles. We're going to draw those in there. Okay. Now notice that the altitude of all three of those smaller triangles that we created are equal, which means that we can inscribe circle I right inside of our triangle from the end center of triangle ABC, so that we now have three radii on circle I. So this is what we constructed. So let's define a few terms. First of all, if we're giving this triangle ABC, we're going to define, let me get a marker. We're going to define line segment AC as side A, line segment BC as side B, and line segment CB as line C. And to find the semi-perimeter, you would just need to add side A plus side B plus side C. All right, let's just erase those terms. Here's our eraser. So side B, side C, added together, divided by 2, would give us half of the perimeter. And now what I want to do is take a minute to look at, we actually created 6 smaller triangles. And I want to prove that the 2 yellow triangles are congruent. So let's look at using side angle side definition. So let's look at triangle AFI and AEI, and we're just going to take a minute to look at the angles and prove that they are true. So we're going to start with angles AF, AI, and EAI, and these 2 angles are indeed congruent because this AI was a bisector, so this makes these 2 angles congruent. Now looking at angle AFI and angle AEI right here, well, by construction these were right triangles because these 2 radii on the circle were created with perpendicular intersectors. And so all angles in a triangle equal 180 degrees. So if this angle is congruent with this angle and this angle is congruent with this angle, then FIA will also be congruent with AIE. So we know the angles are all congruent, but to prove that the triangles are congruent, we need to look at the sides. Well, they share line segment IA, so their side is congruent here. Also, IF and IE were radii on the circle, so we know these 2 are also congruent. And so that also means that AF is congruent with AE. Now, by the same reasoning, we could go through and we could prove that triangle FBI and DBI are congruent, and triangle DCI and ECI are also congruent. And what that gives us, and this is the important part here, is that this side is congruent to this side, and this side is congruent to BD, and DC is congruent to EC. Alright, so now let's change gears for a minute and let's look at this triangle in another way. Let's get an arrow here. So he originally made 3 smaller triangles inside his larger triangle using end circle I. And as we established before, that the formula for finding the area of a triangle is just the base times the height divided by 2. So let's look at this blue triangle to start with, BIC. Well, BIC, we could find the area basically by the base, which is BC, times the height, which is ID, divided by 2. We could do the same thing for triangle BIA. We could use the base, which is AB, times FI, divided by 2 to get the red triangle. And to get the yellow triangle, it would just be line segment AC times the radii of this circle, which is IE, divided by 2. And if we added the blue triangle plus the red triangle plus the yellow triangle, we would get the total of triangle ABC. Now we also established that ID, IE, and IF are all radii on this inscribed triangle, circle inside of this triangle, so therefore they are equal. So now we're just going to use some substitution techniques, and we said that AC was side A, and BC was side B, and AB was side C. So now we're just going to substitute in, and instead of saying BC, we're going to call that B. Instead of saying AB, we're going to call that C. Instead of saying AC, we're going to call that A. And what we're going to use, instead of the 3 different radii, we'll just use one radii, ID. So if we take side A times ID, side B times ID, and times side C times ID, add them up, and we can factor out now our radius, ID, and we're left with side A plus side B plus side C divided by 2, and that looks familiar. That is our semi-perimeter, so this equals S. So if we really wanted to find the area of triangle ABC, we would just need to know the semi-perimeter of this triangle times this radius of this circle. So semi-perimeter times ID will give us the area. So let's do a little bit more construction here. Let's go back to our video. Where are you at? And we're going to construct a little bit more on here. So after we do this, what we want to do is I want to get the semi-perimeter on one line. So let's speed this up, and then we'll talk about what we did here in just a minute. Okay. So this is what I did, is I added line segment CG. Well, BD plus BF, those two are congruent, and DC plus EC, those two are congruent, and AE, and I took this measure right here, AE, and I added it on here, plus EF would give us the perimeter. So right here we have half, 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 and so we have the semi-perimeter from B to G. So we can say that CG is congruent to AE, because that's what I did in the construction. It was just by construction. And if we add BG together, we would get the semi-perimeter, because it's just half of the triangle. So by substitution, and this is going to be important at the end, so remember this whenever I say, oh, you remember whenever we said that the semi-perimeter is just BG, so we could either call this BG or we could just call it S. And the triangle ABC could be found from our previous slide, semi-perimeter times ID, so I'm just going to substitute in and say that BG times ID will now give us our area. Now, we're going to have to go back and we're going to have to construct a little bit more. This will be the last construction. Where are we going? Let's go back to our video. And I'm just going to kind of run through this quickly, and then we'll talk about what happens through this construction. Alright, and here I'm just finding the midpoint of AH so that I can show that that quadrilateral is inscribed in the semi-perimeter of the circle. So now, let's see what that looks like. So what I actually did is we constructed this line IH, which was perpendicular to BI. And also we constructed BI. No. Oh, and we did label point J. Oh, CH. CH right here was perpendicular to our semi-perimeter BG. So we constructed this perpendicular line and we constructed this perpendicular line. And also BH serves as the diameter of this circle. Now, BIH is perpendicular by construction, and BCH is right by construction. So we have two right angles here, and they share a hypotenuse. And because of that, we can say that this quadrilateral BICH right in here, which is half of the is inscribed in half, or the semi-perimeter of this circle, is cyclic, which that's really important because it allows us to define similar triangles within this construction. So what we need to do is just to prove two of these angles are congruent. We know that this angle right here, angle AEI, is a right triangle by construction, and we just said that BCI is right by construction, so we know they share congruent angles here. Now right here, because this is a cyclic quadrilateral, that allows us to prove that angle BHC is vertical to BIC. And so we know that together these add up to 180 degrees. Now if we look at our circle I, there's 360 degrees here. And so back on our construction where we talked about these two triangles being congruent, these two and these two, we showed that these two angles right in here are congruent. So this is half. And then we showed that DIC and EIC were congruent. And so this is half. And then we have BIA and AIE were congruent. And this is half. So if these are vertical angles, then this means that angle AIE is congruent to angle BHC because these are vertical angles. Also, we can look at these two triangles and we can prove that they're similar just by proving two angles. We know by construction that this is a right angle. We know that this angle is by construction is a right angle, so we know those are congruent. And of course those, it's obvious that those are vertical angles, so they are congruent. So we can say that triangle IDJ is similar to HCJ. Now, what these similar triangles allow us to do is to make some ratios. So let's just go through this real quick. BC is to CJ as BC is to AE. Remember, AE was the same as CJ here. And because of this, CH is to IE. Remember, this triangle and this triangle were similar. So CH is to IE as CH is to ID. Now remember, ID is our radius we are looking for because we already know what the semi-perimeter, and semi-perimeter times this ID is going to give us our area. So now we can just substitute that in here. And finally, we can say that this is the same as CJ is to JD. So let's take this formula or ratio comparison here, and we can just jump from B is to C, BC is to CJ, as CJ is to DJ. And what I want to do is I'm going to add 1 to both of these sides. And for this one, I'm going to use CG over CG. And for this one, I'm going to use JD over JD. And adding these together, common denominators. So here's our numerators, here's our denominators. Now, by segment addition, if you will remember that B plus B to C and C to G is the same as B to G. So we can replace this with BG. And C to J and J to D, if we add those up, we get CD. So by substitution, we're going to substitute in our numerator. So we still have an equal ratio. Now what I want to do is I'm going to multiply both sides by 1. And what I want to use for this one is BG to BG, and for this one we'll use BD to BD. Oh, I'm sorry, and this should be a G, not a C. So this should be BG to CG. I don't know how that got changed. So if we multiply, we get BG squared times our denominator. Here's our two terms. All right. Now, the geometric mean on a right triangle. So let's look at this triangle right here. BIJ. By construction, it is right. And we notice that D, which is perpendicular to I, lies on the hypotenuse. So this gives us the geometric mean. So basically, it says that JD times BD is the same as ID squared. And here's our ID, and so now we have it squared. So now, here is, we can say that multiplying JD times BD is the same as squaring ID. So we're going to replace this. And so now we're just going to use cross multiplication. We're just going to cross multiply these terms, and we're going to cross multiply these terms. And to get rid of the square on this side, we'll just square root this side. Now this is starting to look like Heron's formula, so we're getting there. We're almost there. Now by substitution, we can say that this right here, and if you remember, we had that highlighted, that BG, the semi-perimeter, times ID was going to give us the area. So here it is right here, and what we're going to do is we're going to replace that by saying the area of triangle ABC. So therefore, the area of ABC is equal to the square root of these four sides multiplied together. So now, all we need to do, and we're getting there, before we do, let's go back and let's review what the formula looks like that we're trying to prove. So Heron said that the area of a triangle is equal to the square root of the semi-perimeter times the semi-perimeter minus side A times the semi-perimeter minus side B times the semi-perimeter minus side C. And the square root of that, I don't know if I said that. So that looks very similar to what we just did. So here's our area, and then we have these terms. Now, I told you to remember that BG, that line that we drew down at the bottom, is the same as a semi-perimeter. Well, there's BG right there. So that is a semi-perimeter. So all we need to do, well, and there's four terms here. We have S times a term, times a term, times a term, and here we have four terms. Well, here's our S. And so now what we're going to do is we're just going to basically look at this semi-perimeter, B to G, and we're going to use segment addition to figure out how these four terms can be applied from these sides. So let's look at C to G. Here's C to G. It's that red line right there. Well, if we want to get C to G, all we need to do is take the semi-perimeter, which is B to G, and subtract B to C. Now, if you remember, B to C was side B. So, if I want to find CG, all I need to do is take the semi-perimeter and subtract side B. So, by substitution, we're just going to replace that with this term. So, let's look at CD. We already know what BG was. It is S. Okay? So, now let's look at CD. Well, CD is this yellow line right here. So how could we get that? Well, if we took the semi-perimeter, which was BG, and we subtracted out BD and CD. But look, BD is the same as BF, and CG is the same as AF. And so, if I subtract out this blue term and this red term, that is the same as side C. So if I took the semi-perimeter and subtracted side C, I would be left with CD, which is this term right here. Semi-perimeter minus side C is going to give me CD. Now, I'm just left with BD. So here's BD. It's the blue one. All we need to do is take the semi-perimeter, BG, and subtract out CD and CB, which is yellow and red, and which happens to be the same as side A. So if we take the semi-perimeter and subtract out side A, we will get BD. So BD is the same as semi-perimeter minus A. So just substituting in, remembering that this was the same as semi-perimeter minus B, this is the same as the semi-perimeter, this is the same as the semi-perimeter minus C, and this is the same as the semi-perimeter minus A, we end up with Heron's formula. So I hope you've enjoyed this video on how Heron's formula was derived, and thank you very much.